So in this video I'm going to be showing some solutions to a couple of problems in APL and JavaScript and Python. So this week's Perl Weekly challenge tasks were quite array oriented in that they both involve manipulating matrices. Of course, as an APLer this made the tasks fairly straightforward, although maybe my approach to the second task wasn't as array oriented as it could have been because it involves recursion. So what I'm going to do is present my APL approach and then show my attempts at translating solutions into JavaScript and Python. I've got a couple of reasons for using JavaScript and Python. They both have some sort of functional utilities which I can leverage for an array-oriented approach, but also I have started working a bit through Professor Frisby's Mostly Adequate Guide to Functional Programming, and JavaScript is the language it uses to teach functional programming. Now I do a tiny bit of JavaScript, web development, the GUI stuff, so it's not completely alien to me, but I think I agree with Professor Frisby that the main benefit of JavaScript is that it runs by default in most web browsers, and that's kind of like how Python works with Linux. I mean, the other thing with Python is that it was my first programming language, and I'm a bit rusty, so I thought I'd have a go at doing that as well. So I'm going to introduce each task and then talk through my APL solution and then show you how I translated that solution into JavaScript and then Python. And I'll put timestamps in the description so you can skip to specific parts of the video. Okay, so the first task involves taking a numeric matrix as input, and you want to return a matrix of the same shape but where each element is replaced basically by the product of all of the elements in the matrix except for that one. So for example, if I look at element 2, 3, which is a 6 in 3x3 reshape iota 9, then that will be replaced by the product of 1, 2, 3, 4, 5, not 6, 7, 8, 9, like this. So yeah, the problem. So a naive approach is to basically take the vector, or take your input, and create this sort of nested vector by using without for each of the elements. And then you can just take the product of each of those, and that's your answer. But this means, for a large array, you're allocating lots of memory to each of these intermediate arrays, and chasing pointers around and stuff, and it's relatively slow. So we can mitigate this somewhat using the rank operator. So we want to use without rank 99 1 0 rather. So this is the whole of the array without each element of the array. And since we're removing one at a time, we know that we'll have a rectangular thing, so it's always going to be a rectangular result, so that's not a problem, and we can just take a product across the rows like this. If we make sure we ravel our array before processing like this, then we can get a nice rank polymorphic version, so you get the same results but with the shape of the input you give it. And we can also quite easily turn this into tacit form. It's not the best candidate because it's all monadic, but it's not the worst because it's quite simple. And this is an example of what we mean by APL functions being like the inverse of a TARDIS. So the function takes fewer characters to express directly than the number of characters it takes to give it this name. So they're kind of smaller on the inside. Wait, isn't that just a normal box? A normal police box? So this works for the examples that are given, even if we reshape them to 1, 4, 3, like that. So that's pretty nice. But some of you might have noticed that we'll get incorrect results if we have duplicates. Right, so that's not actually quite right. So we can fix this basically by taking the same approach but acting on the indices rather than the elements directly, since we know the array of indices will always be unique. So we can take our little train here, and this is our kind of without indices, the 4 without indices like this. We can use those directly to index into our array. And you can see how we get the same numbers just in a higher dimensional format. So we can again just take the product across. Right, so that's it. Yep. So I'm not an experienced JavaScript programmer by any means, So there might be constructs which make a lot of what I'm doing even more elegant. If you have any ideas for improving, then just let me know. But I'd also be interested to see what a more idiomatically JavaScript approach would be, because obviously I'm just translating my APL solutions. Right, so essentially, and I've got the, can we make this a bit bigger? It's about as far as it'll go. So, I've got the APL expression at the top here. Essentially what I've gone for is doing the same thing, but translating a lot of the primitives that I've used into the JavaScript approach. So, right, so we essentially want to do the same thing. See, in our final function here, we want to generate an array which is our input array, but with each of the elements removed, and then take the product. And that's it. But we're going to do that for each element in our input array. So to do that, I'm kind of cheekily making each iota thing, right? Each iota length of my input array. So product is simply a reduction, a multiply reduction. So that's times slash in APL. And what's this? That's iota. Right, so there's our product. Times slash is iota. Remove from is just using slice to take the top part and the bottom part and cut out the middle. A becomes indices up to a dot length. Let's start with that and our input. Right, so there's 0, 1, 2, 3, 4. Then we're going to map over those indices, and for each index we're going to remove from our input array the element at that index. So there you go, that's our kind of high dimensional, that's our kind of matrix that we're going to do the product over. But whereas in APL you'll do the product on the rows of the whole array together, so you're kind of doing the product on the outside here. In JavaScript, here we have to put the product inside this map. You can see we get the same result. So for Python, I basically just translated the JavaScript because I figured I could get closer a lot quicker. I tried to use NumPy and Func tools to kind of try and make the translation as close in spirit to the original as I could, but I'd say that I didn't quite grok map well enough to use it for the final function, so I ended up using just a for loop. I will say though, at least generating the range of indices is a bit easier in Python, and obviously I quite enjoyed using NumPy's array slicing notation, which is kind of familiar to me from APL. So I guess I can just show you that. Array of thingy. There you go. Clearly some junk going on with floating points, but it doesn't matter. So task number 2 is a kind of array traversal problem. So you want to take some matrix, again in sort of Perl, Raku, Python, JavaScript. This is going to be more like a list of lists. But you want to return an array of the elements in the order as if you've done a spiral around the outside. So I have a demo. So here's our numeric input matrix, and we're basically going to start at the top left and work our way around clockwise, adding or appending each number we come across, or each element we come across, to our result array. So that's 1, 1, 2, 1, 2, 3, 1, 2, 3, 6, 9, 8, 7, 4, 5. So that's the result we're looking for. So I took the approach of starting with a kernel function, which I could then iterate over as I sort of shave the bits of the array off. Yeah, hopefully you'll see what I mean in a second. So I know that I want to start with the first row, but then if I take that first row away, what do I have left and what do I want to get from it? Well, I want the 6 and the 9 next. So that involves rotating the array and transposing it. So now they're at the top and they become the first row. And I can just take the first row of that, and I should be able to do the same thing again. So one drop of that looks like this, and we know we want 8, 7 next. Rotate, transpose, take the first, and there's our 8, 7, etc. So then it was just a matter of encoding that as a recursion. So We say if our array is empty, then we'll just return an empty array. Otherwise, we're going to take our first layer and concatenate that with the transpose reverse one drop. What have I screwed up here? Oops, forgot to actually recurse. There we go. So I guess this one just does one squad omega catenate with the rest of it. That's funny, that. But yeah, so this is my solution. This is the APL solution to the spiral matrix thing. Maybe you'd like to see it with characters instead. So once again, to turn this into JavaScript, I built up some primitives and sort of pieced together the same solution. So JavaScript doesn't have high dimensional arrays. Its arrays are what APLers would call vectors or lists. So a matrix is going to be represented as a list of lists again. Yeah, so I tried looking for a version of transpose which used map, and I did find this one on the internet, but unfortunately it only works for square matrices. And if I give it a rectangular one, transpose, let's say just 1, 2, 3, 4, 5, 6, like this, unfortunately it chops off some elements there. So then I had to revert to the index swapping for loop version that I'm familiar with, or that's pretty obvious. Nested for loop, you just pre-allocate an array of the right size and swap the indices around. And this does work. Can I take this guy and just change that to T? You see we get the sort of axes swapped. I mean, this is equivalent to APL like that. 1, 2, 3 down the column, 4, 5, 6 down the column. But I did sort of realize that a map over the indices is kind of like a for loop. So after a bit of fiddling, I did get one version that uses map and also a reverse function, which I've called R. So, and you can see, again, I need the index generator here. So let's grab that. Oh, that's the version we have here. Right, so yeah, so we got our, so again, we have our index generator. I also made a function which reverses the elements of an array, and I'm pretty happy with how this one turned out, because if I have what I might call a three-dimensional array, so this is two planes, two matrices, each matrix has 2 rows and 3 columns, then we get a sort of similar thing, right? So reversing A will reverse the order of the 2 matrices in the overall array, and if I do a.map R, then this reverses the then this reverses the rows in each matrix, and if I do a.map my row to row.map R, well, then I get the columns reversed again. So yeah, so that's pretty neat. So R transpose, so now I can transpose A like that. Wait, is that the one I put in? Let's pick. Yeah, so there's our transpose, which uses the map and reverse stuff, and if we transpose our array, it gets rearranged like so. So then the last thing to do is basically construct the recursion. So we're saying our matrix becomes, well, if 1 is m.length, then we want to return the first element, right? This is because whereas APL is happy to do slicing and transposing and all this on an empty array at the end and pass that back in where I just spit an empty array back out, JavaScript was not happy about that and was throwing errors, so it's easier to end the recursion when we have one element left and just concatenate that element to the end of the result. Yep. So if we've reached the end, concatenate our final element, otherwise take our first element and concatenate the rest of the stuff with the recursion. You can see we have that represented by a del in APL. In JavaScript we just use the function name. And then slice 1 comma is like a 1 drop, and the map reverse is a reverse on the last axis. So now if I look at spiral matrix A, you can see it kind of works the same way. 1, 2, 3, 6, 5, 4. Okay. So Python and NumPy together have some of the primitives I needed ready to go. So concatenate, transpose, there's actually reverse in there. However, I did notice that reverse, so there is a Python, A is 1, 2, 3, 4. I noticed that reverse A, is that right? A.reverse, that's right, A.reverse modifies the array in place, and I'm trying to take a more functional style for various reasons. So I concocted my own reverse function by wrapping around list reversed, and this reverses my array, which has been reversed, so it'll come out back normal, but it reverses my array without modifying the original. Otherwise, the recursion is pretty much the same, except I had to be more careful about how I sliced and concatenated my pieces than I did in JavaScript. So you can see here I'm not just taking the last element M0, but I'm actually returning a slice, and then I had to use numpy as concatenate with axis 1, so you actually end up with a higher rank array, I think, at the end, and then I kind of fudged it by putting list here and kind of forcing the whole thing into a list. So it's not good, really, but basically time was getting on and I wanted to finish up and make this video. So as a result, I don't think I've made the best use of the functions available, and you can kind of see this in how ugly the solution is. Mainly this part here, mainly the list thing at the end. I'm sure I could have done more to make sure it returned a list properly, but there you go. So by starting from an array-oriented solution, you can see that you get this kind of terse, concatenative programming style. I think that's clearer in JavaScript than it is in Python, but in Python you're kind of restricted by the indentation syntax thing. Some people argue that makes it more readable. I've become less convinced over time, but I'm an APLer, so what are you going to do? I tried to keep it functional where I could, and I think this helps debugging. But also in JavaScript, for example, you could try to integrate the one-letter helper functions back into the overall solution, fold those back in, put it all on the page, and see if you could spot patterns where I'm doing things which could be factored back out and end up simplifying the overall algorithm for this specific case. As it happens, I think, that having these utility functions, it helps me anyway, obviously, because as an APLer, I find it easier to think in terms of array primitives. So that's all for this video. I hope you found it enjoyable or interesting, or both. You can find all of the solutions presented here on my GitHub, which I've linked in the description below. And let me know how you would have done it. And I'll catch you later.